Chemistry, Class 11, Chapter 1. The branch of science that studies the preparation, properties, structure, and reactions of material substances is called chemistry. Importance of chemistry. Chemistry helped in the development of some drugs. Examples are cisplatin and Taxol for cancer therapy and AZT or azithromycin for AIDS. Nature of matter. Anything which has mass and occupies space is called matter. States of matter. Matter can exist in three physical states, namely solid, liquid, and gas. Particles are held very close to each other in solids, and there is no freedom of movement. In liquids, the particles are close to each other, but they can move around. However, in gases, the particles are far apart and their movement is easy and fast. States of matter. Solids have definite volume and definite shape. Liquids have definite volume but do not have definite shape. They take the shape of the container in which they are placed. Gases have neither definite volume nor definite shape. They completely occupy the space in the container in which they are placed. States of matter. The three states of matter are interconvertible. On heating, a solid changes to a liquid, and the liquid on further heating changes to gas or vapor. In the reverse process, a gas on cooling changes to liquid, and the liquid on further cooling freezes to solid. Classification of matter. Matter may be a pure substance or a mixture. In a pure substance, all constituent particles have the same chemical structure. In a mixture, there is more than one type of constituent particle. The pure substances forming a mixture are called its components. A mixture may be homogeneous or heterogeneous. In a homogeneous mixture, the components are uniformly distributed. In a heterogeneous mixture, the distribution is not uniform. Sugar solution and air are examples of homogeneous mixtures. Mixture of salt and sugar and mixture of pulses and sand are examples of heterogeneous mixtures. Pure substances can be classified into elements and compounds. Each molecule in an element contains only one type of atom. Each molecule in a compound contains more than one type of atom. Properties of matter and their measurement. Physical and chemical properties. Every substance has physical and chemical properties. Physical properties can be measured without making a chemical change. Chemical properties can be measured only by making a chemical change. Earlier, English system and metric system from France were used. The International System of Units or SI. The SI system was established by the 11th General Conference of Weights and Measures in 1969. It was created by an organization called CGPM, which was established in Paris in 1875 by the Meter Convention. The SI system has 7 base units. The SI system units: length, meter, mass, kilogram, time, second, electric current, ampere, thermodynamic temperature, Kelvin, amount of substance, mole, luminous intensity, candela. Prefixes used in the SI system: 10 deca, 10 raised to 2 hecto, 10 raised to 3 kilo, 10 raised to 6 mega, 10 raised to 9 giga, 10 raised to 12 tera, 10 raised to 15 peta, 10 raised to 18 exa, 10 raised to 21 zeta, 10 raised to 24 iota, 10 raised to minus 1 deci, 10 raised to minus 2 centi, 10 raised to minus 3 milli, 10 raised to minus 6 micro, 10 raised to minus 9 nano, 10 raised to minus 12 pico, 10 raised to minus 15 femto, 10 raised to minus 18 atto, 10 raised to minus 21 zepto, 10 raised to minus 24 yocto. Mass and weight. Mass is the amount of matter present in an object. Weight is the force exerted by gravity on that object. Mass is constant while weight varies from place to place. In the lab, mass is measured by using an analytical balance. SI unit of mass is kilogram, kg. In the lab, for usual measurements, gram or g is used. Volume. Volume is the amount of space occupied by an object. The SI unit of volume is meter cube. In the lab, milliliter or ml is usually used. 1 meter cube is 1000 liter. 1 liter is 1000 milliliter. Common instruments used in the lab for volume measurement are burette, pipette, graduated cylinder, and volumetric flask. Density. Density of a substance tells us how closely particles are packed in that substance. Density is equal to mass divided by volume. SI unit of density is kilogram per meter cube, written as kilogram meter raised to minus 3. Commonly used unit of density is gram per centimeter cube, written as gram centimeter raised to minus 3. Temperature. The three scales used for temperature are Celsius, Fahrenheit, and Kelvin. Freezing point of water is 0 degrees Celsius or 32 degree Fahrenheit. Boiling point of water is 100 degrees Celsius or 212 degree Fahrenheit. 0 Kelvin is the minimum possible temperature. Negative Kelvin temperature is not possible. The first equation shows conversion between Fahrenheit and Celsius. Fahrenheit is equal to 9 by 5 Celsius plus 32. The second equation shows conversion between Kelvin and Celsius. Kelvin is equal to Celsius plus 273.15. Uncertainty in measurement. Scientific notation. Scientific notation or exponential notation means that any number can be expressed as capital N into 10 raised to small n, where capital N is called digit term and small n is called exponent. Please learn how to add, subtract, multiply and divide exponential numbers. Significant figures. If a value is known with certainty, it is called significant figure. If a value is not known with certainty, it is called uncertainty. In 100, there is only one significant figure. In 100 dot, there are three significant figures. In 100.0, there are four significant figures. In 285, there are three significant figures. In 0.35, there are two significant figures. In 0.3500, there are four significant figures. In 0.0034, there are two significant figures. In 0.000540, there are four significant figures. In 12.0008, there are six significant figures. In 4.21 into 10 raised to 4, there are three significant figures. In 2 eggs, there are infinite significant figures, as it is 2.0000 extended to infinity. Precision is the closeness of various measurements to each other. Accuracy is the closeness of the measurements to the true value. Addition or subtraction of significant figures result cannot have more decimals than the one with least decimals. Multiplication or division of significant figures result cannot have more figures than the number with least significant figures. Here are two examples. First is an addition 12.11 plus 18.0 plus 1.012. The answer is 31.122. 18.0 has only one significant decimal, so the final answer is 31.1. Second example, 2.5 into 1.25 is equal to 3.125. 2.5 has only two significant figures, so the answer is 3.1. Rounding of numbers. If last number is lesser than 5, do not add 1. If last number is more than 5, add 1. If last number is 5, if preceding number is odd, add 1, while if preceding number is even, do not add 1. 1.386 is 1.39. 1.384 is 1.38. 1.385 is 1.38. 1.375 is 1.38. Dimensional analysis. Changing from one unit to another is called dimensional analysis or factor label method or unit factor method. An example is given. 1 inch is 2.54 centimeters. 1 inch by 2.54 centimeter equals 1, and 2.54 centimeter by 1 inch also equals 1. So both of these are called unit factors. Law of chemical combinations. Law of conservation of mass. Put forth by Antoine Lavoisier in 1789. In all physical and chemical changes, there is no change in mass. So matter can neither be created nor be destroyed. Law of definite proportions. Put forth by Joseph Proust. Also called law of definite composition. A given compound always contains the same proportion of elements by weight. An example is given. Cupric carbonate, whether from natural source or synthetic source, has same percentage of copper, carbon and oxygen, as can be seen in this table. Natural sample and synthetic sample both have percentage of copper 51.35, percentage of carbon 9.74 and percentage of oxygen 38.91. Law of multiple proportions. Put forth by Dalton. If two elements can combine to form more than one compound, the masses of one element that combine with a fixed mass of the other element are in the ratio of small whole numbers. An example is given. 2 gram of hydrogen combines with 16 gram of oxygen to produce 18 gram of water. 2 gram of hydrogen combines with 32 gram of oxygen to produce 34 gram of hydrogen peroxide. So, to fixed mass of hydrogen, that is 2 gram, the masses of oxygen that can combine are 16 gram or 32 gram. These form the ratio of 16:32 or 1:2. Gay-Lussac's law of gaseous volumes, put forth by Gay-Lussac in 1808. When gases combine in a chemical reaction, they do so in a simple ratio by volume. An example is given. Hydrogen 100 ml combines with oxygen 50 ml to produce water 100 ml. Volume of hydrogen and oxygen has the ratio 100:50, that is 2:1. Avogadro's law. Equal volumes of all gases at the same temperature and pressure should contain equal number of molecules. Dalton's atomic theory. Atomio means indivisible. Democritus, a Greek philosopher, originated the idea. Dalton, in 1808, proposed that matter consists of indivisible atoms. This idea was proposed in his book, A New System of Chemical Philosophy. Atomic and molecular masses. Atomic mass. Earlier, hydrogen was given a mass of 1. In 1961, this was changed. Carbon-12 was given a mass of 12 atomic mass units or AMU. Carbon-12 is one of the isotopes of carbon and is represented as 12C. So now 1 AMU is defined as 1 by 12 the mass of one carbon-12 atom. 1 AMU is actually 1.66056 into 10 raised to minus 24 gram. Presently, AMU is replaced by unified mass denoted as U. Average atomic mass. Average atomic mass takes into account the relative abundance of various isotopes of the element. Isotope A has AMU of A and abundance of X percentage. Isotope B has AMU of B and abundance of Y percentage, and isotope C has AMU of C and abundance of Z percentage. Average atomic mass is AX percentage plus BY percentage plus CZ percentage. An example is shown here. Carbon 12 isotope, abundance 98.892 percentage, 12 AMU atomic mass. Carbon 13, abundance 1.108 percentage, atomic mass 13.00335. Carbon 14, abundance 2 into 10 raised to minus 10. Atomic mass 14.00317. From the above data, the average atomic mass of carbon will come out to be 0.98892 into 12 unit plus 0.01108 into 13.00335 unit plus 2 into 10 raised to minus 12 into 14.00317 unit equal to 12.011 units. Molecular mass. Molecular mass is the sum of masses of all atoms in the molecule. Molecular mass of methane, that is CH4, is equal to, since one carbon atom, the AMU of carbon, that is 12.011 U, and since 4 hydrogen atoms, 4 into 1.008 U, that is 16.043 U. Formula mass. In some substances like sodium chloride, there are no separate molecules. The atoms are arranged in a 3D way as seen in this image. Here we know that for every atom of sodium, there is an atom of chlorine. So we use sodium chloride NaCl, and instead of the term molecular mass, here we use the term formula mass. It is calculated in the same way as molecular mass. Thus, the formula mass of sodium chloride is atomic mass of sodium plus atomic mass of chlorine. That is 23U plus 35.5U equal to 58.5U. Now there is a problem. Calculate the molecular mass of glucose, that is C6H12O6. The solution: 6 into mass of carbon plus 12 into mass of hydrogen plus 6 into mass of oxygen. That is 6 into 12.011 plus 12 into 1.008 plus 6 into 16, that is 180.162 units. Mole concept and molar masses. If the atomic mass of a molecule is X grams of the substance is called 1 mole. The symbol is MOL. It contains exactly 6.022 into 10 raised to 23 molecules. This number is called Avogadro constant or Avogadro number. Symbol is capital N and a subscript capital A. Since atomic mass of water is 18.02, 1 mole of water is 18.02 gram. This is called molar mass of water. It contains exactly 6.022 into 10 raised to 23 molecules of water. Percentage composition. Let us take an example to understand what this is. Water is H2O. Percentage composition of hydrogen in water is the weight of water molecule contributed to by hydrogen. Thus, it is 2 into atomic mass of hydrogen divided by atomic mass of water. That is 2 into 1.008 by 18.02 into 100, that is 11.18. Let us take one more example. What is the percentage of carbon, hydrogen and oxygen in ethanol? Molecular formula of ethanol is C2H5OH. Molar mass of ethanol is 46.068 gram. Mass percentage of carbon is 2. There are 2 carbon atoms, so 2 into atomic mass of carbon divided by the atomic mass of ethanol, that is 52.14. Now mass percentage of hydrogen, there are 6 hydrogen atoms, so 6 into atomic mass of hydrogen divided by atomic mass of ethanol, that is 13.13 percentage. There is 1 atom of oxygen, so mass percent of oxygen is atomic mass of oxygen divided by atomic mass of ethanol, that is 34.73 percentage. Empirical formula and molecular formula. Empirical formula is the simplest whole number ratio of various atoms in a molecule. Molecular formula is the exact number of various atoms in a molecule. A compound contains 4.07% hydrogen, 24.27% carbon and 71.65% chlorine. Its molar mass is 98.96 gram. What are its empirical and molecular formulas? Now the molar mass is 98.96 gram. 4.07% of this is hydrogen. So hydrogen mass in 1 mole of the compound is 4.07% into 98.96, that is 4 gram. This is 4 moles of hydrogen since 1 mole of hydrogen is 1 gram. Similarly, carbon mass in 1 mole of the compound is 24 gram. This is 2 moles of carbon since 1 mole of carbon is 12 gram. Also, chlorine mass in 1 mole of the compound is 70 gram. This is 2 moles of chlorine since 1 mole of chlorine is 35 gram. Thus 1 mole of the compound has 4 moles of hydrogen, 2 moles of carbon and 2 moles of chlorine. The simplest whole number ratio is 2:1:1. So empirical formula is 2 hydrogen, 1 carbon and 1 chlorine, and this is written as CH2Cl. The mass of empirical formula is called empirical formula mass. This is molar mass of carbon plus 2 into molar mass of hydrogen plus molar mass of chlorine, that is 50 gram. Here molar mass divided by empirical formula mass is 100 gram divided by 50 gram, that is 2. So molecular formula is 2 times the empirical formula, that is 2 times CH2Cl, that is C2H4Cl2. Stoichiometry. In Greek, stoichio means element and metry means measurement. Stoichiometry refers to calculation of masses of reactants and products of a chemical reaction. Consider this balanced chemical reaction. CH4 plus 2O2 gives CO2 plus 2 hydrogen, that is methane burns to produce carbon dioxide and water. All these are in gaseous forms as shown by the G in brackets. On the left side are the reactants and on the right side are the products. G in brackets denotes gas, S is for solid and L is for liquid. 2 for oxygen and water are called stoichiometric coefficients. It is 1 and so not denoted for methane and carbon dioxide. From the equation we can understand the following things. One molecule of methane reacts with two molecules of oxygen to produce one molecule of carbon dioxide and two molecules of water. 1 mole of methane, that is 16 gram, reacts with 2 moles of oxygen, that is 2 into 32 equal to 64 gram, to produce 1 mole of carbon dioxide, that is 44 gram, and 2 moles of water, that is 2 into 18 is equal to 36 gram. We know that 1 mole of any gas occupies 22.7 liters. Thus, 22.7 liters of methane reacts with 45.4 liters of oxygen to produce 22.7 liters of carbon dioxide and 45.4 liters of water. Limiting reagent. The reactant that is present in least amount gets consumed first, and then further reaction cannot take place even if other reactants are present. The reactant that gets consumed first limits the reaction, so it is called limiting reagent. Reactions in solutions. The amount of a substance in a solution can be denoted in many ways. One way is mass percent. Mass percent is equal to mass of solute by mass of the whole solution into 100. For example, if 3 gram of salt is added to 7 gram of water, the mass percent is 3 by 10 into 100. Another way is mole fraction. Mole fraction is number of moles of the solution divided by total number of moles in the solution. For example, if a solution is made of substances A and B, then mole fraction of A is equal to number of moles of A divided by total number of moles in the solution, that is number of moles of A divided by number of moles of A plus number of moles of B. Similarly, mole fraction of substance B is equal to number of moles of B divided by number of moles of A plus number of moles of B. Molarity. Molarity is the number of moles of the substance in 1 liter of the solution. It is denoted as capital M. It is the most widely used unit. Molarity is equal to number of moles of the substance divided by volume of the solution in liters. When a solution in water is diluted, the equation M1V1 is equal to M2V2 can be used. For example, we have 1 liter of 1 molar solution of sodium hydroxide. To make it 0.2 molar solution, how much water is to be added? Now 1 into 1 is equal to 0.2 into V2. So V2 is equal to 1 divided by 0.2, that is 5. So we have to make it a 5 liter solution. So 4 liters of water has to be added. Another question. 4 gram of sodium hydroxide is added to water to make up 250 ml of water, 250 ml of solution. What is the molarity of the solution? Molar mass of sodium hydroxide is 40 gram. So 4 gram of sodium hydroxide means 1 by 10 moles of sodium hydroxide. So 1 by 10 moles of sodium hydroxide is present in 250 ml of the solution. So 4 by 10 moles of sodium hydroxide should be present in 1 liter of the solution. So the molarity is 4 by 10 or 0.4. Another method is molality. Molality is the number of moles of the solute in 1 kilogram of the solvent. It is denoted by small m. Molality is equal to number of moles of the solute divided by mass of solvent in kilogram. Density of 3 molar solution of sodium chloride is 1.25 gram per milliliter. Find the molality. 1 milliliter of the solution weighs 1.25 grams. So 1 liter of the solution weighs 1250 grams. Now we know that 1 liter of the solution has 3 moles of sodium chloride because the molarity of the solution is 3. So 1 liter of the solution has 3 moles of sodium chloride, that is 3 into 58.5 gram, because 1 mole of sodium chloride is 58.5 gram, that is 175.5 gram. So 1 liter of the solution has 175.5 gram of sodium chloride, or in other words 1250 gram of the solution contains 175.5 gram of sodium chloride. So the weight of water is 1250 minus 175.5 gram, that is 1074.5 gram of water. In kilogram, 1.0745 kilogram of water. So molality is 3 divided by 1.0745, that is 2.79. Development of chemistry. Chemistry initially developed as a result of search for two things: philosopher's stone or paras, which would convert all baser metals like iron and copper into gold, and search for elixir of life, which would grant immortality. Alchemy and iatrochemistry were the forms of chemistry in 1300 to 1600 AD. Modern chemistry took shape in 18th century Europe. In ancient India, chemistry was called Rasayan Shastra, Ras Tantra, Ras Kriya, or Ras Vidya. Examples of chemistry in ancient India are baking of bricks, making pottery with fire, use of gypsum cement in construction work, making faience glass, increasing hardness of copper by adding tin and arsenic, coloring of glass by using metal oxides, tanning of leather, dyeing of cotton, and production of salt from sea. Gypsum is a mixture of sand and lime, that is calcium hydroxide with lesser amount of calcium carbonate. Rashopanishada is an ancient Indian text which describes preparation of gunpowder. Nagarjuna was a great Indian chemist. His work Ras Ratnagar deals with mercury compounds. He has also discussed methods for the extraction of metals like gold, silver, tin, and copper. Rasarnavam, a book, discusses the uses of various furnaces, ovens, and crucibles. It describes methods by which metals could be identified by flame color. Chakrabani discovered mercury sulfide. The credit for inventing soap also goes to him. Varahamihir's Brihad Samhita is an encyclopedia of 6th century AD. It describes the preparation of glutinous material from plants to be applied on walls and roofs, and also describes perfumes. Gandhayukli also describes perfumes. Acharya Kanda, 600 BC, originally known by the name Kashyap, was the first proponent of the atomic theory. He called them Paramanu. He authored the text Vaiseshika Sutras. Kanda stated that there are many types of atoms. Charaka Samhita is the oldest Ayurvedic text of India.